Hi, good day everyone. We are here to discuss to you the rules in assigning oxidation states. So, we will discuss to you the basic rules of assigning oxidation states, and at the end of the video, after we are finished discussing, we will give a few examples for you to test what you have learned. So stick around until the end of the video. The oxidation state or oxidation number of an element in a simple binary ionic compound is the number of electrons gained or lost by an atom of that element when it forms the compound. If we were to relate it with the periodic trends of the periodic table, the most electronegative element, or in other words, the element with the highest tendency of attracting a bonding pair of electrons, is assigned a negative oxidation state, while on the other hand, farther to the other side, a positive oxidation state is assigned. A set of rules are presented when assigning oxidation states. In general, oxidation states are always assigned on a per-atom basis. The rules that are to be discussed are categorized into two for the sake of simplicity and are separated to general and specific rules. In the general rules, for an atom in its free, uncombined element, its oxidation state is equivalent to zero. The idea of a free uncombined element is defined as either the element is by itself or the element is connected with copies of themselves. This means, for example, that the oxidation state of Na or sodium is zero because it is by itself and is not bonded with other elements. Another example are the oxidation states of H2 and O2, which are both zero. Their oxidation states are equivalent to zero because they are connected with copies of themselves only. Another general rule states that for an ion, the oxidation state is equivalent to the total charge. Breaking this down, this also means that the oxidation state of a neutral compound such as H2S or hydrogen sulfide is equivalent to zero. Furthermore, the sum of the oxidations of every atom in a certain compound is equivalent to the total charge of the atom. For example, NO3 negative or nitrate has a total charge of -1 by summing up the oxidation states of each atom in the compound. To prove such claim, we shall now proceed to the more specific rules. Okay, so hydrogen, at most cases, has an oxidation state of +1, unless it is combined with metals or boron, which results to it having -1 as an oxidation state. Some examples include NaH or sodium hydride and CaH2 or calcium hydride. Since sodium and calcium are both metals, when one of them pairs with hydrogen, the oxidation state of hydrogen becomes -1 instead of +1. Now, oxygen, as the second most electronegative element, usually has an oxidation state of -2 in its compounds, but it has a few exceptions. The oxidation state of oxygen becomes -1 in peroxides in the form of X2O2, or -1/2 in superoxide in the form of XO2, where in both cases, X is a group 1A element such as hydrogen, lithium, sodium, and potassium. Its oxidation state switches to +2 if it is paired with the most electronegative element, fluorine, which has an oxidation state of -1. With reference to the periodic table, group 1A and 2A have oxidation numbers of +1 and +2 respectively in all of their compounds. Group 3A elements have oxidation states equivalent to +3. Group 5A, 6A, and 7A elements have oxidation numbers of -3, -2, and -1 respectively in binary compounds with metals, with H, or with NH4+. If such conditions were not met, their oxidation states can be determined by referring to the general rules. Okay, So to test the rules that we have just learned, let's go through some examples. Feel free to pause the video so you can answer by yourself and check if you understood. Okay, so in number 1, we have to look for the oxidation state of P in P4. So because it is a free, uncombined element, its oxidation state is equal to 0, based on the first general rule we discussed. In the second item, we have to look for the oxidation state of oxygen in H2O. In H2O, the oxidation state of oxygen can be found by solving for it like a variable. Hydrogen here has an oxidation state of positive 1 multiplied by 2 because there are 2 hydrogen atoms in H2O. Then we transpose to get the oxidation state of oxygen, which we can see is negative 2. Okay, so moving on to the next item, we have to look for the oxidation state of hydrogen in LiH. Referring to the first specific rule discussed, when hydrogen is paired with a metal, its oxidation state is equal to negative 1. So we have the answer. Okay, so in item number 4, we have to look for the oxidation state of oxygen in OF2. Now in this case, we refer to the second specific rule discussed. It stated that the oxidation state of oxygen is positive 2 when paired with fluorine, which has negative 1 as an oxidation state. So when we solve for the oxidation state of oxygen, when F2 has an oxidation state of negative 2, we get positive 2. Okay, moving on to the next item, we have to look for the oxidation number of oxygen in Na2O2. In this case, we have a peroxide. It has a form of X2O2 where X is Na and Na is a group 1A element. So this gives O2 the oxidation state of negative 1 based on the specific rule number 2 that we discussed. Okay, now in item number 6, we have to look for the oxidation state of oxygen in RbO2. Now, in this case, we have a superoxide. It has a form of XO2 where X is Rb and Rb is a group 1A element as well. This gives oxygen the oxidation state of negative 1/2 based on the specific rule number 2 that we have discussed. Now in item number 7, we have to look for the oxidation state of N in NH3. Here, we solve for the oxidation state of N by referring to the first specific rule. It was discussed that hydrogen has an oxidation state of positive 1 in compounds unless bonded with metals. But in this case, N is not a metal. So we solve for its oxidation state, we get a negative 3. Okay, now for the last item, we have to look for the oxidation state of S in SO2. So we solve for the oxidation state of S by using negative 2 as the oxidation state of oxygen. Because in this case, S is not a group 1A element, it is a group 6A, so it can't be a peroxide. Solving for it, we get positive 4. Okay, so that's it guys. Thank you for listening and thank you for sticking around. We hope that we have helped you in learning a few things about assigning oxidation states. That's it. Goodbye.